Welcome to Science to Sleep By. Settle in, take a deep breath, and let the quiet hum of the cosmos guide your thoughts tonight. As you rest, imagine yourself floating far beyond the noise of daily life, past the moon, past the planets, into the deep sea of stars where silence becomes infinite. Tonight's story comes from one of humanity's most powerful eyes on the universe, the James Webb Space Telescope, a machine so sensitive it can detect the faint heat of stars born billions of years ago. But with great vision comes unsettling revelations. As JWST peers deeper into the universe than any instrument before it, it's finding objects, structures, and cosmic behaviors that shouldn't exist, shaking the foundations of astrophysics and leaving astronomers whispering the same question: is this JWST's most terrifying discovery yet? Let's drift into that mystery together. In the quiet vastness of the cosmos, where time stretches like a soft fabric, and distance becomes a gentle, endless horizon, the James Webb Space Telescope has revealed something that has left astronomers wide awake at night, even as you drift toward sleep. When JWST opened its golden mirrors to the early universe, it expected to find small, faint, newly forming galaxies, cosmic infants just beginning to assemble themselves out of hydrogen clouds. Instead, it found giants, enormous galaxies that appear fully formed, massive, and mature at a time when the universe was still in what should have been its earliest, most fragile developmental stage. These galaxies aren't just puzzling, they are timeline-breaking, physics-challenging, and foundation-questioning. They represent a category of object that current cosmology simply has no room for, prompting many astronomers to call them the most unsettling structures ever discovered from this era. What makes these galaxies so terrifying isn't their size alone, but the epoch in which they appear. According to the standard model of cosmology, the universe began 13.8 billion years ago, and for hundreds of millions of years, it was too hot, too chaotic, and too unstructured for galaxies to form. Only after the cosmic dark ages lifted around 550 to 800 million years after the Big Bang did the first small galaxies emerge like tiny sparks flickering in the darkness. But JWST has found galaxies that appear only 300 to 400 million years after the Big Bang, and they aren't small. They are enormous, containing as many stars as the Milky Way, or more. For perspective, imagine observing a newborn that is somehow already 6 feet tall, fully grown, muscular, and speaking complete sentences moments after birth. That is the scale of impossibility JWST is presenting to cosmology. These early galaxies are not only large, they are surprisingly dense. The stars within them appear packed into tight regions, far more compact than modern galaxies. This density implies that star formation happened extraordinarily quickly, far quicker than existing theories allow. The gas clouds that collapse to form stars typically take hundreds of millions of years to cool, settle, and ignite. Yet these galaxies seem to have done it in a cosmic heartbeat. Their brightness and mass suggest they formed stars at a rate that should have been impossible given the early universe's temperature, pressure, and chemical composition. Hydrogen and helium, the universe's first ingredients, were supposed to create slower burning, less efficient early stars. But somehow these galaxies appear to have formed stars almost explosively, as if something jump-started their growth. Astronomers studying these galaxies have raised an unsettling possibility that almost feels like a whisper of a forbidden idea. Maybe the physics that governed the early universe is not the same physics we see today. JWST's data challenges more than just the timing of cosmic evolution. It hints that our models for star formation, gravity, gas cooling, and dark matter behavior may be incomplete. If these galaxies truly exist as JWST observes them, then either matter clumped together far faster than expected, or there were processes at work that accelerated cosmic structure formation in ways scientists don't yet understand. Some researchers have even suggested that dark matter, this invisible skeleton holding the universe together, may behave differently in the earliest epochs, forming gravitational wells more rapidly than our equations predict. Adding to the mystery, some of these galaxies appear to host surprisingly evolved stellar populations. Their colors indicate that the stars inside them may have lived, burned, and died before the universe was even 500 million years old. This would require multiple generations of star formation, supernova explosions, and chemical enrichment, a process that should take billions of years, not hundreds of millions. Heavy elements like carbon, oxygen, and iron seem to be present in amounts that defy expectations. If confirmed, this would force scientists to reconsider the entire timeline of chemical evolution in the universe. In a sense, these galaxies behave like time travelers, carrying maturity into an era where only primitive structures should exist. One of the most haunting aspects of JWST's discovery is how many of these anomalously massive galaxies it has found. If there were only one or two, astronomers might call them statistical outliers or observational errors. But there are too many to dismiss. Each new deep field image Webb takes seems to reveal another impossibly massive galaxy staring back at us from the dawn of time. This abundance implies that something fundamental is missing from our understanding of the cosmos. The standard model of galaxy formation is not built to handle a universe that grows this quickly, organizes this efficiently, or creates complexity this early. Some cosmologists have floated the idea that our measurements of distance and age might be off, that redshifts could be misinterpreted under certain conditions. Others think new physics may be required, exotic forms of dark matter, modified theories of gravity, or unknown energy processes that catalyzed galaxy growth. The early universe may not have been the slow, gradual unfolding we once imagined. Instead, it may have been a turbulent, hyper-efficient engine of creation, producing large-scale structures almost immediately after the first light appeared. These galaxies stand as cosmic contradictions, silent, ancient witnesses to a universe that may have behaved far more violently, far more aggressively, and far more rapidly than our models ever predicted. When you look at these early galaxies, glowing softly across 13 billion years of space and time, they carry with them a quiet but undeniable message. They are the first hint that the universe we live in might not be the universe we thought we understood. That earliest moments of cosmic history may hold secrets we are only now beginning to glimpse, and that some of the most terrifying discoveries are the ones that tell us everything we thought we knew may need to be rewritten in the gentle stillness of the night. When thoughts drift like distant stars across the mind, the James Webb Space Telescope reveals something far more unsettling than bright galaxies from the cosmic dawn. It reveals order where there should be chaos, structure where there should be formlessness, and gravitational harmony in an era when the universe was still a turbulent sea of hot gas. As astronomers examined the earliest snapshots captured by JWST, they noticed that some of the young galaxies and clusters did not grow in the slow, gradual way predicted by cosmological models. Instead, they appeared tightly bound, neatly arranged, and gravitationally stable. The problem is that such stability requires dark matter, far more dark matter than theories say should have existed in those early regions. And without that extra invisible mass, the structures JWST is detecting simply should not be able to hold themselves together. To understand why this is so unnerving, consider how galaxies normally form. Dark matter is believed to make up most of the universe's mass. It does not shine or absorb light, yet it exerts gravitational pull. In the standard model of cosmology, dark matter forms the scaffolding upon which galaxies eventually take shape. Invisible halos of dark matter gather first, drawing gas into their gravity wells and allowing stars to form. This is meant to be a slow, step-by-step process unfolding over hundreds of millions of years. In the early universe, the first few 100 million years, there should not have been enough time for large, well-defined dark matter halos to develop. But JWST's images show galaxies and galaxy-like structures that appear already cradled in deep gravitational basins, as if dark matter halos pre-assembled themselves with astonishing speed. These unexpected structures force astronomers to ask a question that borders on cosmic heresy. Is dark matter behaving differently in the early universe? Or is our understanding of gravity incomplete? When JWST's infrared vision peers back in time and sees galaxies that are already stable, dense, and mature, it suggests that the invisible architecture beneath them formed more rapidly than any known model predicts. That rapid assembly implies either dark matter clumped together faster than theory allows, or that some other unknown mechanism created deep gravitational wells long before the universe should have been able to support them. Even more unsettling, some of the early cosmic structures appear to be too organized. Instead of chaotic gas clouds slowly settling into place, JWST has revealed rotationally supported disks, neatly aligned stellar populations, and signs of early galactic mergers that require well-developed gravitational environments. These features would normally appear only in galaxies that have had billions of years to evolve. Yet JWST is seeing them within a few 100 million years of the Big Bang, leaving astronomers struggling to reconcile observations with equations. If gravity behaved exactly as it does today, then the amount of dark matter required to explain such early order would need to be dramatically higher. But increasing the amount of dark matter in the early universe would break nearly every other prediction cosmology makes about the cosmos. The gravitational behavior of these early structures is especially confusing because dark matter interacts almost exclusively through gravity. It does not collide, heat up, or radiate energy. For it to clump rapidly, something must have made it come together faster than standard models allow. Some scientists propose that early dark matter might have been colder, meaning it moved more slowly and clumped more efficiently. Others suggest the existence of exotic forms of dark matter, such as self-interacting dark matter, that could allow halos to collapse more quickly. Still others wonder whether the universe experienced a phase of accelerated matter clustering, driven by processes we have not yet identified. In each scenario, the rules that govern dark matter today would not be the same rules that governed it in the first billion years. One of the most dramatic examples involves the formation of early galaxy clusters, large collections of galaxies bound together by gravity. JWST has spotted structures resembling protoclusters far earlier than any previous telescope could detect. These clusters contain galaxies that seem to interact gravitationally in coordinated ways, suggesting the presence of massive dark matter halos. But forming such massive halos requires enormous amounts of time. Yet there they are, emerging from the universe's first few 100 million years, as if they had somehow skipped ahead in cosmic evolution. These observations push astronomers into uncomfortable territory, where they must question whether our timeline of structure formation is fundamentally wrong. Another surprising feature is the presence of gravitational lensing around early galaxies. Gravity bends light, and strong lensing indicates dense regions of mass. JWST has observed lensing effects around galaxies that should not be heavy enough to bend light significantly. This suggests that either dark matter halos around these galaxies are much denser than predicted, or that some unknown source of mass is contributing to the gravitational field. Lensing is one of the most reliable tools in cosmology, and seeing it in the early universe with such strength raises questions that ripple through every layer of astrophysical theory. As astronomers continue examining these baffling structures, they are confronted with a cosmic puzzle that seems to deepen rather than resolve. If dark matter gathered too quickly, then the early universe could not have expanded and cooled in the way predicted by standard cosmology. If gravity behaved differently, then the equations that describe everything from planetary motion to the dynamics of galaxy clusters might be incomplete. And if the structures themselves formed through processes we have not yet recognized, then the early universe may have operated according to rules that faded away as the cosmos aged, leaving only these ancient, quiet relics for JWST to uncover. When the James Webb Space Telescope extends its gaze into the quiet depths of cosmic history, it uncovers structures that seem far too grand, too coordinated, and too mature for the early universe. Among these revelations, perhaps none is more haunting than the sight of immense cosmic filaments stretching across space in an era when the universe should have been young, scattered, and unorganized. These filaments, long, thread-like strands of gas, dark matter, and emerging galaxies, are part of what scientists call the cosmic web, the vast interconnected skeleton upon which the universe builds itself. Normally, these webs take billions of years to form, evolving as gravity slowly pulls matter into delicate threads and nodes. But JWST has detected early versions of these structures, appearing far earlier than physics predicts, hinting at forces and processes that may have shaped the universe in ways we do not yet understand. In the standard picture of cosmology, the cosmic web emerges gradually from tiny fluctuations in the early universe's density. These fluctuations were barely measurable imbalances, small ripples left over from the Big Bang's turbulent expansion. Over immense stretches of time, gravity amplified these ripples, pulling matter together in long strands while emptying out vast voids between them. The result, after billions of years, is the large-scale structure we observe today: galaxies grouped in clusters and filaments surrounding enormous, empty cosmic bubbles. But JWST's observations introduce a disquieting complication to this long, slow, orderly process. It has captured evidence of filament-like arrangements less than 500 million years after the universe began, a period when matter should have still been in chaotic motion and far too diffuse to form anything resembling a cosmic web. What makes this anomaly so striking is not just the presence of early filaments, but the scale and organization they appear to show. JWST images reveal what seem to be aligned galaxies, elongated structures of gas, and narrow channels of matter arranged in patterns that echo the cosmic web's modern shape. These early filaments are not as extensive or as dense as those seen in the mature universe, but their very existence challenges fundamental expectations. To form them so quickly, matter would have had to clump more efficiently, collapse more rapidly, and organize itself with a precision that standard cosmology cannot easily explain. A particularly unsettling detail is the apparent maturity of some of these structures. In certain early JWST images, galaxies seem to be strung along these filaments like beads, spaced in ways that suggest gravitational interaction and collective evolution. This level of coordination typically requires long periods of gravitational attraction, yet, in the epochs JWST is probing, there simply shouldn't have been enough time. Simulations of early structure formation, which rely on the well-tested equations of gravity and dark matter dynamics, do not produce anything close to what JWST is observing. To make these filaments appear so early, something in the universe must have accelerated their formation, whether through unknown physics or through processes yet to be identified. One hypothesis being considered is that the early universe may have been more efficient at forming structures due to properties of dark matter that no longer exist today. If dark matter in its earliest state behaved differently, perhaps interacting more strongly with itself or with normal matter, it could have created gravitational channels sooner. These channels would then act as early scaffolding, enabling gas to flow along them and galaxies to form in linear arrangements. Another possibility is that the universe's early expansion rate might have differed slightly from predictions, allowing it to cool and settle more quickly into patterns of gravity-driven organization. Even slight tweaks to the expansion history could dramatically alter the timeline for filament growth. There is also growing discussion around the influence of primordial magnetic fields. These hypothetical magnetic fields, if strong enough, could guide the flow of gas in the early universe, assisting in the formation of elongated structures. Though this idea remains speculative, it reflects the lengths to which scientists are being pushed as they attempt to explain JWST's findings. If magnetic fields played a larger role in the early cosmos, they could have sculpted gas into narrow channels long before gravity alone was capable of doing so. Another aspect of the cosmic web anomaly concerns the relationship between early filaments and galaxy formation. Galaxies do not form randomly across the sky. They tend to appear where the cosmic web is densest. JWST's evidence of galaxies already aligned along filament-like structures suggests that these galaxies may have been born inside gravitational channels that were present almost immediately after the cosmic dark ages. This scenario contradicts the expectation that galaxies emerged first and filaments only later emerged to connect them. Instead, it suggests that the framework existed before the galaxies themselves, acting as a cosmic guide for the earliest stages of structure formation. The dimensions of some of these filaments are also surprising. JWST has observed structures spanning hundreds of thousands of light-years, a scale that should take billions of years to assemble under normal gravitational evolution. In a universe still in its infancy, there simply should not have been enough time for matter to travel the distances required to form these extended networks. This raises questions about how quickly matter could move, cool, and settle in the early cosmos. Some researchers propose that early matter may have flowed with surprising coherence, guided by gravitational forces stronger or more complex than currently understood. What troubles cosmologists most deeply is that these anomalies are not isolated. The more JWST looks into the earliest epochs, the more it sees hints of structure and organization. Instead of a universe slowly assembling itself from a primordial fog, JWST reveals a cosmos that appears to have snapped into order with surprising speed. These early filaments may represent the universe's first attempts to build a large-scale framework, but their existence challenges the timeline and mechanisms that cosmology has relied on for decades. If filaments really did form this early, then the early universe may have been a far more dynamic, interconnected, and rapidly evolving place than anyone previously imagined, whispering through its ancient light that the story of cosmic structure may need to be rewritten from the beginning. Among the many quiet puzzles the James Webb Space Telescope has uncovered, few stir the imagination or unsettle astronomers quite like the sight of supermassive black holes appearing in places they should not exist. In the deep, gentle darkness of the early universe, JWST has detected the unmistakable signatures of tremendous gravitational beasts, each millions or even billions of times the mass of the Sun, shining through the glow of hot gas spiraling into their depths. These black holes are ancient, forming astonishingly soon after the Big Bang. Yet what shocks researchers most is not just their age or their size. It is the fact that some of them appear to exist without the massive galaxies that should surround them. They are giants without homes, gravitational titans, wandering the early cosmos like solitary shadows, challenging the long-held belief that black holes form within galaxies, not before them. For decades, astronomers believed galaxies created the environments necessary for supermassive black holes to grow. In the modern universe, these huge black holes sit at galactic centers, surrounded by dense clouds of stars and gas that feed them over billions of years. Their existence depends on the gravitational environment provided by the galaxy itself. It was assumed that a black hole could reach enormous size only after a galaxy had time to assemble and evolve. Yet JWST is showing us black holes that existed when the universe was less than 500 million years old, a time when galaxies should have been tiny, chaotic, and starved of the ingredients needed to create such massive objects. The traditional view of black hole growth begins with small seeds, perhaps the remnants of the first stars, which collapse into black holes a few dozen or a few hundred times the mass of the Sun. Over time, these seeds accrete gas, merge with other black holes, and gradually grow. But the process is slow. Even in ideal conditions, growing from a stellar mass black hole to a supermassive one takes hundreds of millions or billions of years. Yet JWST has found black holes as massive as those in the contemporary universe, when the cosmos was still a cosmic infant. This rapid growth defies the timeline astrophysics has relied upon. Something must have accelerated their formation. Either the seeds were much larger than expected, or the early universe offered conditions unlike anything we observe today. One explanation gaining traction is that the early universe may have produced black holes directly from the collapse of massive gas clouds, skipping the intermediate steps entirely. These so-called direct collapse black holes could begin their lives at around 100,000 solar masses, allowing them to grow much more quickly. But even these models struggle to explain the sheer number of giant black holes JWST is finding, and more disturbingly, the fact that some of them appear isolated or lightly hosted. In many cases, JWST detects bright quasars, luminous beacons generated by matter falling into supermassive black holes, but the surrounding galaxies appear faint, underdeveloped, or missing entirely. This leads astronomers to suspect that black holes may not just grow within galaxies. They may shape them. If this interpretation is correct, the early universe may have operated in reverse from what scientists long believed. Instead of galaxies forming first and black holes emerging later, the earliest black holes may have served as the gravitational anchors around which galaxies assembled. Their immense gravitational pull could have drawn gas inward, creating the conditions for star formation and structure growth. This flips the cosmic script, suggesting that black holes were architects, not byproducts, of early galaxies. The implications are profound. It means that black holes could have existed before the earliest galaxies took shape, roaming the primordial universe as solitary engines of gravity. JWST's precision has allowed astronomers to estimate the age and distance of these early black holes, discovering that some of them appear to have formed only 200 to 300 million years after the Big Bang. This is so early that the first stars themselves had only begun to ignite. For black holes of this size to exist at such timescales, either the universe grew structures far faster than expected, or something else contributed to black hole formation on a scale not yet understood. Some researchers propose that primordial black holes, hypothetical black holes formed directly from the collapsing densities of the Big Bang itself, could explain JWST's observations. These objects, if they exist, could have varied widely in size, with a few growing into supermassive black holes long before the first galaxies formed. Though highly speculative, this idea is gaining renewed interest in light of JWST's findings. Another mystery is why some of these early black holes appear so active. The gas around them is heated to extreme temperatures, generating light bright enough to outshine entire galaxies. Yet the galaxies themselves appear small or underdeveloped, as though the black hole's intense radiation might have stunted their growth. High-energy emissions from quasars can blow gas away from galaxies, preventing star formation and leaving faint, disrupted structures behind. If early black holes were unusually active, they may have consumed gas faster than galaxies could use it to form stars, essentially starving their host galaxies. This would create a universe populated by black holes far more massive than the structures surrounding them, a picture eerily similar to some of JWST's observations. There is also the question of location. Some of these black holes appear offset, not centered within galaxies as they are in the modern universe. This displacement suggests dynamic, violent origins, perhaps black hole mergers or gravitational recoil events powerful enough to kick black holes out of their host galaxies. If black holes in the early universe merged frequently, the resulting collisions could have launched them into intergalactic space, leaving behind faint trails of disrupted stars. JWST may be detecting some of these wandering giants as they continue consuming gas in isolation. The existence of rogue supermassive black holes, or even supermassive black holes without fully formed host galaxies, poses a challenge to nearly every model of cosmic evolution. It forces scientists to reconsider how matter moved, cooled, and collapsed in the earliest epochs. It raises questions about whether the first stars, the first galaxies, and the first structures formed in the order long assumed, and it suggests that the universe's early history may have been dominated by gravitational engines so powerful and so efficient that they shaped the cosmos before many other structures even had time to appear. As the James Webb Space Telescope peers into the earliest ages of the universe, it does so by reading the faint, stretched-out glow of ancient light. This glow carries with it the fingerprints of time, motion, and cosmic distance. Astronomers rely on a phenomenon known as redshift to understand how far away an object is and how long ago its light began its journey toward us. In the simplest terms, the more the universe expands, the more the wavelengths of light stretch, shifting toward the red end of the spectrum. This makes redshift one of the most essential tools in cosmology, a kind of cosmic clock built into the fabric of space itself. But JWST's unprecedented sensitivity has uncovered light whose redshift values do not align with any cosmological predictions, plunging astronomers into what is now being called the redshift crisis. These puzzling observations raise difficult questions about whether the universe's expansion, composition, or even geometry behaves differently from what we thought. At the heart of this crisis are galaxies and structures that appear far older or more massive than their redshifts should allow. When light from distant objects reaches JWST, its spectrum tells astronomers how much the universe has stretched since that light was emitted. Higher redshift means earlier cosmic time. For the future, JWST's discovery means decades of new research. It means simulations will be updated, models recalibrated, old theories rephrased. Entire research fields may shift their focus toward these impossibly early cosmic giants. Students today may spend their entire careers working through the consequences. And still, the universe will continue revealing itself with patient, indifferent beauty. JWST is only one step in this long journey, but its discoveries have opened a door that cannot be closed again. And now, with the quiet of deep space echoing through these new observations, we find ourselves standing at the threshold of a slightly larger, slightly older, slightly stranger universe. One that waits for us to continue listening to it with curiosity, humility, and wonder. As we arrive gently at the end of this journey, the universe feels a little wider, a little older, and a little more mysterious than it did before. JWST's most terrifying discovery, whether it is an ancient galaxy too massive for its age, a structure too organized for the early cosmos, or a glow born from processes we still cannot name, has not plunged us into confusion. Instead, it has guided us into a deeper calm, the kind that comes from realizing that the universe is far more intricate than our early theories allowed. The cosmos has always carried secrets in its earliest light, and now, with JWST lifting the veil more than any telescope before it, we find those secrets waiting patiently for us to understand them. What began as a pursuit of clarity has become a meditation on how much more there is to learn. Each anomaly JWST unveils is not a warning, but a whisper, a reminder that the universe did not begin as a simple place. It began in complexity, in intensity, in rapid transformation, in structures that formed faster and burned brighter than expected. These revelations do not break our scientific foundations. They deepen them, stretching our understanding in directions that open new questions, new theories, and new possibilities. They invite us to take our time, to breathe with the cosmos, rather than trying to force it into familiar shapes. This discovery, unsettling as it may first seem, ultimately brings a peaceful humility. It shows that science is not a race toward certainty, but a slow, continuous unfolding of truth across generations. It reminds us that awe is part of the process, that mystery is not a flaw, but a feature of the universe we inhabit. And as we picture these ancient lights crossing more than 13 billion years to reach us, we can rest in the wonder of knowing that the cosmos is far larger and more layered than anything we once imagined. JWST has illuminated not only the distant past, but also the path ahead, a path lined with questions that will guide astronomers, dreamers, and listeners into futures where curiosity remains our brightest instrument, shining softly in the dark.